Okay, section 22. This section combines the previous two sections, talking about goodness of fit hypothesis tests and two-way tables. So, first the theory, and then in a second video we'll do an example. So the idea is that we start with a two-way table. We have two categories that we're comparing. Let's say that it's men and women on the one hand, sex, and left-handedness or right-handedness on the other. And we would like to know whether the observed counts for the people we actually have suggest that these two ideas are related in general. So now we're doing inference. That is, in section 21, we were talking about what's actually going on in the data itself. Now we want to infer things about the general population from which this was taken. 900 people, they're either men or women, they're either left-handed or right-handed. There may or may not be some relationships going on in this particular data, but are they significant enough that they suggest that something is going on in general? Does the data suggest that what sex you have and whether you're left-handed or right-handed have nothing to do with one another? Or does the data suggest that men are more likely to be left-handed or women are more likely to be left-handed, etc., etc.? In other words, either it is plausible that the two variables have nothing to do with one another, that they're independent, or maybe we have evidence that the two variables do have something to do with one another. The key word there is something. Now, if two variables have nothing to do with one another, then you know the relationship between them. There isn't one. On the other hand, if they have something to do with one another, then that's very plural, right? You don't know the relationship between them. If it is not the case that what sex you are and what handedness you are have nothing to do with one another, then they have something to do with one another. Men are a little more likely to be left-handed. Men are a lot more likely to be left-handed. Women are more likely to be left-handed. All sorts of things could be true if the singular idea of independence is not the case. So in other words, having nothing to do with one another, being independent, is an H0 kind of thing, a particular understanding of the facts. Having something to do with one another to some degree, in some way, or some other way, is an HA kind of thing. It's plural. So that's the key to understanding what we're doing. But again, the basic idea is, do the relationships, things are probably not going to land dead center in the tables. If you've got a weird count like 17, then it may not even be possible for things to land dead center because these have got to be whole numbers. But nevertheless, do any imbalances that you happen to see in the sample you happen to be looking at suggest that there's a relationship in general for the broader population, or are they simply the luck of the draw? For the particular sample we happen to have, maybe we happen to get a lot of left-handed men. Does that suggest that men are more likely to be left-handed, or is it just the luck of the draw for this particular sample? This is, as usual, the kind of thing that hypothesis tests can separate out. As always, hypothesis tests only tell you how unlikely a particular sample would be on your given assumptions. In other words, they separate out pure random chance from things that are too unlikely to be pure random chance, causing you to rethink your assumptions. So with all that in mind, we can make a start on this. We have a two-way table, data, taken from a broader population. And as always, the sample you look at may be typical or it may be very unusual, and you have no way of knowing that without knowing what's going on in the population, and of course you don't. All you can do is play the odds. So in this case, our H0 is that the two variables are independent. Again, having nothing to do with one another is a known relationship. In this particular example, whether you're left-handed or right-handed is got nothing to do with whether you're male or female. HA is that the two variables are dependent, that they are related in some way to some degree, something other than having absolutely nothing to do with one another, something other than having nothing to do with one another, a very plural kind of thing, not the kind of thing you can assume for the purpose of running the numbers. Again, if they have nothing to do with one another, then you understand the relationship between them, and you can run the numbers based on that. If they have something to do with one another, then that opens up the whole next question of what they have to do with one another, and to what degree, and so forth and so on. We talked about this back in section 4, right? You could say, for the sake of argument, that the weather here and the weather in London have absolutely nothing to do with one another. That whether it's raining here and whether it's raining in London, knowing one doesn't really shed any insight into the other, for all practical intents and purposes. On the other hand, the weather in Albany versus the weather in Schenectady, a few miles to the west, well, if it's raining here, then it's more likely to be raining in Schenectady. If it's a sunny day in Schenectady, it's more likely to be a sunny day here. You see the point? If two things have nothing to do with one another, how does knowing the weather in Albany change your opinion of the weather in London, what it may or may not be? It doesn't. It has no bearing whatsoever. How does knowing that it's a sunny day in Albany change the likelihood that it's this, that, or the other weather in Schenectady? Well, get a PhD in meteorology. You see my point? If two things are related, then it becomes very complicated, the relationship between them. But if two things are unrelated, then that is a known piece of information that you can go with. So the H0, the null hypothesis in this case, has got to be independence. If the two variables have absolutely nothing to do with one another in general, how weird is it to pick a sample where they happen to be as related as they are? Is it just the luck of the draw, or is it too unlikely to be the luck of the draw? Which suggests that yes, rethink your idea. Maybe they are dependent in some way. If you pick 1,000 people, and all the men are left-handed and all the women are right-handed, then that would definitely suggest that handedness has something to do with sex. On the other hand, if the counts are a tiny bit off, slightly more women are right-handed and slightly less men are right-handed, then maybe it's just the luck of the draw in that sample. So you see, it is the deviance from independence. It is how different the sample is from what you would expect if they were independent, which suggests that they are dependent. If the relationship in what you happen to be looking at is very strong, then it suggests a relationship in general in the population. If it's not all that strong, then independence in the broader population is still plausible. In the end, this is a specific type of goodness of fit test. We call it the chi-square independence test, and we think of it as a separate test, but really it's just building on the goodness of fit test in section 20. And I think I've pretty much said all this, but let's just read it anyway. The logic is as follows. If the two variables were independent in the population, what counts would you expect under ideal conditions in a sample of that size? Example, let's say that 10%, for the sake of argument, let's say that 10% of people are left-handed, 90% of people are right-handed, and that whether you're male or female has absolutely nothing to do with that, independence. Well, then if you picked 500 men and 500 women, you'd expect 10% of the men to be left-handed and 10% of the women to be left-handed. 50, 450, 50, 450. That is how that would play out for a sample of that size if the variables were independent and if your sample happened to land dead center. So in the end, we're comparing the chart we actually have to that ideal chart that you would expect to have if things were independent and you landed dead center. Does our actual table differ significantly from that table of expected counts that you would get if things were independent? how unlikely is it that we get a count as out of alignment as we did from what you'd expect if the variables were independent? That is to say, assuming the variables are independent, how unlikely is it that you would get a table as out of alignment with the ideal? If it's very out of alignment, then rethink the idea that those things are independent. If it's just a little bit out of alignment, then independence is still plausible. So as always, it's the p-value. The p-value in this case represents the probability of getting a sample as out of alignment, at least as out of alignment with the ideal you would expect if the variables were independent. The lower the p-value, the harder it is to believe you'd get a sample this weird, this out of alignment with the ideal, if the variables had nothing to do with one another. As always, a low p-value means we reject H0. The only major difference is that, as in section 20, our hypotheses are not quite the way they played out in the previous sections, equality, less than or equal to, and so forth. These are a little tedious in practice because you've got to compute a large number of things. The bottom line is that this is an ordinary goodness of fit test where first we have to figure out the expected counts for each of these, quote, categories. In this case, cells. Once you have figured out the expected counts, once you have figured out what you would ideally expect in each cell, if the two variables were totally unrelated and your sample happened to land dead center, once you've figured out that ideal table, then it plays out pretty much exactly the way the previous goodness of fit test did. The only difference is the degrees of freedom formula is a little bit exotic, and we'll talk about that in a minute. So what are the expected counts? Well, cell for cell for cell for cell in the table, in the ideal table you're trying to create, the expected counts are the row total times the column total divided by the total total, the corner total. Now this makes perfect sense if you think about the way independence plays out, and we'll talk about that a bit later. But the bottom line is, for each of those cells, you compute that. Of course, we'll do an example. Then, as usual for the goodness of fit test, we compute the chi-square statistic. Cell for cell for cell for cell, however many cells you have, you get observed minus expected, square it, divided by expected, and add them up. And as always, these are positive things. Counts are, well, the bottom is expected, the bottom are counts, so they're positive, and the top is squared, so that's positive. So, as we talked about in section 20, and for exactly the same reasons, we're adding up a bunch of positive things to get a positive statistic. The same old right-tailed chi-square statistic. Same table, same chi-squared. Only difference is we've got a little bit more work to get to those expected counts rather than being given them at the start of the problem. The degrees of freedom is the number of rows minus 1 times the number of columns minus 1. The reason for this is, and you can figure this out with a little experimentation, if you know the counts in any sub-table, minus 1 row and 1 column, then you could theoretically figure out the remaining counts in that last row and last column. If you knew the rest of the counts and the totals, then you could theoretically fill in that last row and that last column. So that's the reason it is the way it is, but the bottom line is that's what it is. So if you have 3 categories in the one and 4 categories in the other, 3 and 4, then it's going to be 3 minus 1 times 4 minus 1. That's the ideal. Of course, if you didn't have that many cells, it would be a little tedious, but that's the ideal. Then, as always, we look up the corresponding chi-square statistic. Either we use a calculator, and it's the same calculator that we used last time. I've put a couple of them on here. I don't remember if that was before or after the section 20 video, but there are a couple of chi-square calculators to choose from here. Or you could ballpark it the way we did the t-values. We talked about it both ways, I think, in section 20, and we'll do it both ways here. So from there, it plays out pretty much exactly as before. A low p-value, lower than, say, 5%, means that you reject independence. Otherwise, independence is still plausible. Don't reject it. So I'm not going to do this full example out, but I just want to justify our previous work, and then we'll do a more interesting example in a separate video. To understand this formula, let's take an example. Suppose 10% of people are left-handed, and suppose, let's say that this is independent of gender. So pretty much exactly what I was saying before, only I've done a less intuitive count here. So we look at 900 people. For the sake of argument, whether you are male or female has nothing to do with whether you are right-handed or left-handed. So then if we take a sample of 400 men and 500 women, then this is what we would expect to find. If it is true that 10% of people are left-handed, and if it is true that that has nothing to do with whether you're male or female, then when you look at 400 men, you'd expect 10% of them, 40, to be left-handed, and the rest to be right-handed. And for the women, if you look at 500 women, then you'd expect 10% of them, 50, to be left-handed, and the rest to be right-handed. So you get the idea? If we look at 400 men and 500 women for a total of 900 people, and if it is true that handedness is independent of sex, then we could figure out these counts. So that is the ideal. If you look at 900 people, and 400 of which are men and 500 of which are women, and if handedness is independent of sex, and if your sample landed dead center, the ideal, then this is the table you would expect to get. Of course, you may not necessarily get whole numbers here, and as in section 20, that's okay. You use what you use. Don't round them for the sake of rounding them. If they have to be something other than whole numbers, then it doesn't really matter. It's just an ideal to work with. The point is, it may not even be possible to get whole numbers, right? For a weird sample size like 877, these may not work out to be whole numbers. So it may not be theoretically possible for a sample to land, quote, dead center. And even if it were, it probably wouldn't. For a large sample, if you look at 1 million men, you're probably not going to get 100,000, 100,000 left-handed. It's just too on the nose, right? So you are going to deviate from this ideal table. The sample is going to deviate from this ideal table. For the same reason that if you flip a fair coin 1 billion times, you're not going to get exactly 500 million heads. It probably won't be very different, but it probably won't be exact either. So you're not going to land dead center on your actual sample, but the extent to which cell for cell for cell for cell, on balance, on totality, the extent to which you deviate away from this ideal sample is the extent to which independence becomes suspicious and gives you grounds to reject it. That's the idea. A large chi-square value, which in turn represents a small tail, represents in the first place a big deviation from this ideal, and therefore makes it harder to believe independence. Now, as for why this formula works the way it does, remember that A and B are independent is the same thing as saying that that the probability of A and B is the probability of A times the probability of B. We didn't actually define it this way, but we did show that it was an equivalent definition. If A and B are independent, then this is true. If this is true, then A and B are independent. It comes to the same thing. So with that in mind, we can do this as probability. Remember, to get probabilities out of this, you just divide by the relevant totals, as we've seen. What's the probability that you are a man and left-handed? Well, if you're picking one of these 900 people, then you've got to pick one of those out of one of those, right? So the probability that you are a left-handed man, if you pick one of these 900 people, the probability that you get a left-handed man is the total successes over the total you're picking from, as always, 40 divided by 900. So you see, cell divided by corner total is the probability that you pick one of these, or if you prefer, the proportion of what you've got that is one of these. It's the same thing, right? So the probability that you're a man and left-handed is 40 out of 900. Now the probability that you're a man is total men out of total you're picking from, 400 out of 900. And the probability that you're left-handed is 90 total left-handed out of total 900. So if the independence principle played out for this particular cell anyway, then what you would expect is that 40 over 900 would be the same as 400 over 900 times 90 over 900. And if the two concepts in general were independent, then that would be true for every one of those 4 cells here, or however many cells you've got, not counting the totals. Now if you cancel out one of those 900s and rearrange things a bit, this is the same as saying, well, cancel out, say, this one and this one. Then that's the same as saying that 40 is that times that divided by that. And where does that take us back to? So having canceled out, let's say, this 900 here, we're left with this, 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 and this. So that's the same as saying that the cell total is the same as the one corner total times the other corner total divided by the total. Try again. The cell total is the same as the row total times the column total divided by the corner total, the total. So if that is true, cell for cell for cell for cell, if that is true for every cell, then that is what independence represents. So rather than taking this approach in order to fill in our table, we could take this approach to create our table. In other words, we're jury-rigging it from the existing table. Start with the totals that you actually have, and then reverse engineer using that formula what you would expect to find in these cells. Now bear in mind that these row totals and column totals don't represent much of anything, right? The fact that there are 400 men and the fact that there are 500 women has nothing to do with whether men and women are more likely to be left-handed. It just has to do with how many men you happen to pick and how many women you happen to pick. Likewise, this is how many left-handed people you happen to have and how many right-handed people you happen to have. So those don't necessarily represent anything, but you can reverse engineer what you would expect to find in here if the two concepts were unrelated. That's the theory, and we'll do a separate video for the actual example.